Hello guys, welcome you all for today's class. Today we are going to discuss about Maxwell relations and TDS equations. In our previous class, we have derived four Maxwell relations on the basis of mathematical relations. First, we have derived mathematical relations, then we have derived four Maxwell relations. So now today we will, with the help of these Maxwell relations, we will derive very famous two TDS equations. One is based on the internal energy and another is based on the enthalpy. These both are thermodynamic potentials. So these TDS equations are applied in so many applications because a lot of manipulation, permutation, combinations are available to derive different types of equations by using these two TDS equations. Even in Clausius-Clapeyron equation, Joule-Thomson, Joule-Kelvin expansion process during heating and for refrigeration purpose, a throttling valve is required, and throttling valve work under the Joule Kelvin expansion. So these are very important relations. So we are going to first we define these four Maxwell relations because we will take help of these four Maxwell relations during derivation of the TDS equation. So first we write once again we remind you about four Maxwell relations based on these four thermodynamic potentials. So let us first write these four Maxwell relations. So first one is internal energy function du equal to TDS minus PdV, and Maxwell relations is based on this one del T over del P at constant S equal to minus sign because there is a one minus sign. So del P over del S at constant V. This is the first Maxwell relations based on the internal energy thermodynamic potential. This is a thermodynamic potential U, and second one is based on enthalpy. So dH equal to TDS and plus VdP. Corresponding relation will be del T over del P at constant S equal to del V over del S at constant P. This is the second Maxwell relations. Third one is dF Helmholtz function. It is a minus PdV minus S dt. So this one corresponding this Maxwell relation is del P over del P over del T at constant V equal to del S over del V at constant T. This is a third Maxwell relations, and fourth one is based on the Gibbs energy function dG equal to VdP minus S dt. So corresponding Maxwell relation in differential form will be del V over del T at constant P equal to minus sign del S over del P at constant T. This is a fourth relation. So these are four relations that we are going to use in derivation of the TDS equation. So first, that's why I have reminded you, minimize its size and replace it this point. These are four relations. So for reference purpose, we put here in corner. Now we derive first TDS equation. So let us see based on the internal energy. It is based on the internal energy thermodynamic potential U. So we know that first we take because U is a function of, we can write temperature and volume. We know that internal energy is function of temperature and volume. You can write U, internal energy per unit mass, is a function of temperature and volume. Already we know that internal energy is a point function and it is a state function and it depends upon the temperature and volume. So we can write differential equation form du equal to del u over del t at constant v dt and plus del u over del v at constant t dv. This is the question number 1. And we know that this, let us see what is this quantity. If we say del u or del t, according to definition of the specific volume, specific heat at constant volume. So it is a rate of change of internal energy per at constant volume per unit change of temperature. This is a Cv. Nothing. It is a Cv. So du equal to Cv dt and plus del u over del v at constant t. Now already we have derived one equation. You see here du equal to TdS minus PdV from Maxwell relation. This one, take this equation. So du equal to TdS minus PdV. So comparing these two equations, comparing these two equations 1 and 2, you see that this quantity must be equal to this one. So Cv dt equal to TdS. Cv dt equal to TdS. So Cv by T equal to ds by dt. You can write del S over del T at constant, because for constant volume. So del S by del T at constant volume equals Cv by T. This is a equation. Now we take again. Now already we have considered the usual function of temperature and volume. Now we can define S is a function of entropy, is a function of temperature and volume, because it is also function of temperature and volume. So ds equal, again we differentiate with respect for S, for exact differential. ds equal, we can write ds equal to, by using mathematical relation that already we have derived, we have discussed. So ds equal to del S over del T at constant V dt and plus del S over del V at constant T now dV. This is equation number 3. Comparing equation, now putting value. We have derived value del S over del T at constant V. From here, you can take this value from here and put this value here. That is equal to ds equal to Cv by T and dt and plus del S over del V at constant T dV. Now we see from equation, now we have to replace this one. This quantity we have to replace. Watch it in 4 Maxwell relations where it see del S over del V at constant T. This one. Del S over del V at constant T equal to del P over del T at constant V. So replacing this value from here by using Maxwell's third relation for Helmholtz function, we can replace del S over del V at constant T equal to del P over del T at constant V. So ds equal to Cv by T dt and plus del P over del T at constant P, at constant V, not T, at constant V dV. Multiplying by T, so we get equation, now replacing this. So multiplying by T, TdS equal to Cv dt and plus T del P over del T at constant V dV. This is a first TdS equation. This one is a first TdS equation. That we have derived with the help of the 4 Maxwell relations. In this case, we have used third Maxwell relations for replacing this value. Del P over del T at constant V, we have replaced del P over del T at constant, del S over del V at constant T, we have replaced it by del P over del T at constant V. So we get, this is a final TdS equation. TdS equal to Cv dt plus T del P over del T at constant V dV small change in volume at constant here del P over del T at constant V. This one is a first famous TDS equation. Now we derive second TDS equation. Second TDS equation. For second TDS equation, so here we considered H. H is a function of temperature and pressure. Already we know that enthalpy. What is enthalpy? Enthalpy means total heat content in which pressure energy is also involved. That's why and it depends upon temperature also. So pressure and temperature are two main parameters on which enthalpy depends. So let us here define H is a function of temperature and pressure. So dH equal to differentiated dH equal to T in partial form del H over del T at constant P dt as del H over del P at constant T dP. This is again equation number 1, and we know that this we can write in this form dH equal this equation we can see. Here we can see what is this value. Del H over del T at constant P, it is a Cp, it is a enthalpy. Del H over del T at constant P equal to Cp. So dH we can write dH equal to Cp dt and plus del H over del P at constant T dP. This is equation number 2. Again we know that dH from you can see from this equation dH equal to TdS plus VdP. Comparing these two equations, because these are same equations, dH equal to TdS plus VdP. So this here you can see VdP, and so let this parameter you can check. So Cp dt equal to by comparing these two equations you can find Cp dt equal to TdS, and here you can see ds over dt equal to Cp by T. We can write this equation del F over del T at constant P equal to Cp by T. This we have to remember del F over del T at constant P equal to Cp by T. So replacing this one over del T at constant P equal to Cp by T. Now again considering, because we have considered H is a function of the T and P. Similarly we can take function S is also function of the T and P. Temperature and pressure. Entropy is also function of temperature and pressure. So now differentiate ds. ds equal to del T over del P. Del T you can write ds equal to del F over del T at constant P dt plus del F over del P at constant T dP. This is equation number 2. So now putting del S over del T at constant P from this relationship, already we have defined del S over del T at constant P equal to Cp by T. Replacing this value from this value, so ds equal to Cp by T dt and plus del S over del P at constant T dP. Now comparing this parameter from Maxwell relation, you can see from fourth Maxwell relation, this one we have taken for the Gibbs energy function. So replace del S over del P at constant T from here. Del S over del P at constant T equal to minus del V over del T at constant P. Replacing this value from here, you can write ds equal to Cp by T dt minus del V over del T at constant P dP. Multiplying this equation by T, so you get TdS equal to Cp dt minus T del V over del T at constant P dP. So this one is a second TdS equation. So we got two TdS equations. This one is second TDS equation. So I think it is clear that these two TDS equations we have derived with the help of four Maxwell relations, and there are infinite number of possibilities that you can derive so many number of the. We have done these two TDS equations and four Maxwell equations, and further we can, because among these parameters, among temperature, volume, pressure, entropy, we can form so many number of the relations. So there are, it requires very uh, rigorous practice to get mastery over finding all kind of relations based on these pressure, volume, Maxwell relations. So it is a tedious process, but these two tedious equations are very, very important, because by using these two tedious equations we can define Cp minus Cv equal to R, one of the most famous relation that is known as the Meyers relationship. Because it has a very inside information about properties of the matter, real gases and ideal gases property we can define on the basis of Meyer's formula. By using these two TDS equations, we can derive Cp minus Cv equal R in our next class. Thank you very much for watching. If you like it, please make a comment and subscribe and share it. Thank you very much and have a nice day.